Number 1. The Bootstrap Paradox. Information without origin. The concept of causality serves as the bedrock upon which human understanding of reality is constructed, a linear progression where every effect must inevitably trace back to a preceding cause. This fundamental law of physics and logic dictates that nothing can exist without an origin point, a moment of creation that sets the chain of events into motion. Yet buried within the theoretical frameworks of time travel and closed time-like curves lies a disturbing anomaly that threatens to unravel this very fabric of existence. It is known as the Bootstrap Paradox, a self-contained loop of information or matter that possesses no discernible beginning, effectively existing outside the traditional constraints of cause and effect. Imagine a scenario where a traveler journeys back in time to deliver a manuscript of a famous symphony to a composer who has not yet written it. The composer, believing the work to be a gift from the muses or perhaps a forgotten draft of their own, copies the notes exactly and publishes the piece under their name, achieving worldwide acclaim. Decades later, the time traveler discovers this published score, takes it back to the past, and delivers it to the composer once again. The question that plagues physicists and philosophers alike is deceptively simple, yet profoundly unsettling. Who actually composed the music? The traveler did not write it, for they merely copied what they found in the future. The composer did not write it, for they merely transcribed what was handed to them from the future. The information exists in a perpetual cycle, stable and consistent, yet completely devoid of an original creator. This is not merely a plot device for science fiction narratives, but a genuine mathematical possibility within the solutions of Einstein's field equations, specifically those involving Gödel metrics and wormhole topology. In such a universe, information becomes an ontological ghost, haunting the timeline without ever having been born. The implications extend far beyond lost symphonies. Consider the transmission of critical scientific data or biological code. If a future scientist sends the blueprint for a cure to a pandemic back to a researcher in the past, and that researcher uses it to save humanity, the knowledge itself has no point of invention. It simply is. This violates the second law of thermodynamics in a subtle but catastrophic way, suggesting that entropy can be bypassed in closed loops, allowing information to remain pristine forever, without the degradation usually associated with the passage of time. Some theorists argue that such paradoxes are proof that backward time travel is impossible, that the universe must possess a mechanism, perhaps akin to the Novikov self-consistency principle, which prevents any action that would create a logical inconsistency. However, others posit that the universe is far stranger than our linear intuition allows, capable of sustaining these causal loops as stable features of space-time geometry. If the Bootstrap Paradox is real, it suggests that creativity and discovery are illusions, that what we perceive as innovation might merely be the recycling of information from a future that has already happened. It forces us to confront the terrifying possibility that our entire history, our greatest achievements, and our most profound insights might be nothing more than echoes bouncing around a closed circle, never originating, never ending, just eternally repeating. The stability of such a loop implies a deterministic universe where free will is an impossibility, for every action taken within the loop was always destined to happen to maintain the consistency of the timeline. There is no branching path, no alternative outcome, only the rigid, unbreakable circle of existence. As we delve deeper into the mysteries of quantum mechanics and the nature of time, the Bootstrap Paradox stands as a monolithic warning sign, indicating that our current understanding of reality is woefully incomplete. It challenges the notion of progress, suggesting that the arrow of time might not point forward at all, but rather curve back upon itself, trapping us in a narrative with no author. The silence of the origin point is deafening, leaving us to wonder if anything we know truly belongs to us, or if we are merely custodians of secrets passed down from a future we have yet to create.
Number 2. The Fermi Paradox, the silence of the cosmos. The night sky stretches above us, a vast and glittering expanse containing hundreds of billions of stars in our galaxy alone, each potentially hosting worlds of their own. Given the sheer scale of the universe and the age of the cosmos, the mathematical probability suggests that intelligent life should not only exist, but should be abundant, widespread, and unmistakably evident. Yet, when we scan the heavens with our most sensitive instruments, when we listen to the cosmic radio spectrum for signals of technology, when we search for the telltale signatures of Dyson spheres or atmospheric pollution from industrial civilizations, we encounter only a profound and unsettling silence. This is the Fermi Paradox, named after the physicist Enrico Fermi, who famously asked during a casual lunchtime conversation in 1950, "Where is everybody?" The question, deceptively simple, cuts to the heart of our understanding of life, intelligence, and the trajectory of technological civilizations. If the universe is teeming with life, as the Drake equation suggests it might be, then even at sublight speeds, a single advanced species could colonize the entire galaxy within a few tens of millions of years, a blink of an eye in cosmic terms. The fact that we see no evidence of such colonization, no von Neumann probes replicating in our asteroid belt, no artificial structures dimming distant stars, no intercepted communications, implies one of several disturbing possibilities. Perhaps intelligent life is extraordinarily rare, a cosmic fluke that has occurred only once, here on Earth, making us not just special, but utterly alone in a universe that appears designed for solitude. Or perhaps the window for technological civilization is tragically brief, that societies inevitably destroy themselves through nuclear war, ecological collapse, or the unchecked development of artificial intelligence before they can achieve interstellar communication or travel. This is the Great Filter hypothesis, suggesting that somewhere along the evolutionary path from simple organic molecules to galaxy-spanning civilizations, there exists a barrier so formidable that almost no species passes through it. The terrifying implication is that this filter may lie ahead of us, not behind, meaning that our current technological adolescence might be the prelude to an inevitable extinction event that silences all emerging civilizations before they can broadcast their presence to the cosmos. Alternatively, perhaps advanced civilizations deliberately choose to remain hidden, adhering to a galactic prime directive that forbids interference with developing worlds. Or perhaps they have transcended physical existence altogether, uploading their consciousness into substrates beyond our detection, communicating in ways our primitive senses cannot perceive. Some theorists propose that we are living in a simulated reality, that the absence of extraterrestrials is a deliberate feature of the simulation, designed to isolate us for observation or experimentation. Others suggest that the very nature of intelligence leads to inward focus, that once a civilization masters its own psychology and virtual environments, the urge to explore the cold, empty void of space diminishes, replaced by the infinite landscapes of inner experience. The paradox deepens when we consider the timing of our own emergence. Earth is a relatively young planet in a relatively young galaxy. Perhaps we are simply the first, the pioneers who have arrived before the cosmic party has truly begun. But this optimism is tempered by the realization that if we are first, we bear an immense responsibility, that our actions now could set the template for all life that follows, or that our failure could extinguish the flame of consciousness before it has a chance to spread. The silence of the cosmos is not merely an absence of data, it is an active, pressing question that challenges our assumptions about progress, survival, and the ultimate fate of intelligence. Every passing year of silence, every null result from SETI, every exoplanet discovered in a habitable zone that shows no signs of technology adds weight to the possibility that something fundamental about our understanding of life and civilization is wrong. The Fermi Paradox forces us to confront the possibility that the universe is not a bustling marketplace of ideas and cultures, but a vast, empty cathedral where humanity whispers into the void, unsure if the walls are listening or if there are any walls at all. As our technology improves and our search becomes more sophisticated, the paradox only grows more acute, transforming from a casual question into a looming existential riddle that may define the trajectory of our species for centuries to come.
Number 3. The Black Hole Information Paradox, the erasure of reality. At the event horizon of a black hole, the known laws of physics collide in a catastrophic contradiction that threatens to undermine the very foundation of quantum mechanics and general relativity. According to Einstein's theory of general relativity, a black hole is defined solely by its mass, charge, and angular momentum, a principle known as the no-hair theorem, which suggests that all other information about matter that falls into the black hole is irretrievably lost to the outside universe. However, quantum mechanics dictates a fundamentally different reality, one where information can never be truly destroyed, where the evolution of a quantum system must be unitary and reversible, preserving the complete history of every particle interaction. This irreconcilable conflict is the black hole information paradox, first articulated by Stephen Hawking in the 1970s, when he demonstrated that black holes are not entirely black but emit thermal radiation, now known as Hawking radiation, which causes them to slowly evaporate over immense timescales. The paradox arises because this radiation appears to be completely random, carrying no imprint of the matter that originally formed the black hole or fell into it. If a black hole evaporates completely, leaving behind only thermal radiation, then the information about everything it consumed would be permanently erased, violating the principle of quantum determinism and suggesting that the universe is fundamentally unpredictable at its deepest level. This is not a mere academic disagreement. It strikes at the heart of whether reality is consistent, whether the past can be reconstructed from the present, whether the laws of physics are truly universal. For decades, physicists have grappled with this problem, proposing increasingly exotic solutions. Some suggest that the information is not lost but encoded in the subtle correlations of the Hawking radiation, released slowly as the black hole evaporates, though the mechanism for this encoding remains elusive and mathematically contentious. Others propose that the information is stored on the event horizon itself, in a holographic projection, where the three-dimensional volume of the black hole is described by a two-dimensional surface, a concept derived from the holographic principle and string theory. This would mean that reality as we perceive it might be a projection, a shadow of deeper, more fundamental processes occurring at the boundaries of space-time. More radical interpretations suggest that black holes do not evaporate completely, but leave behind stable remnants, microscopic objects containing vast amounts of information, though such remnants would require new physics to explain their stability and infinite internal states. Another possibility, equally unsettling, is that the information escapes into a baby universe, a branching spacetime that pinches off from our own, meaning that every black hole might be a gateway to a new cosmos, but at the cost of losing that information forever from our observable reality. The implications extend beyond theoretical physics. If information can be destroyed, then the concept of entropy, of cause and effect, of memory and history itself becomes unstable. The universe would possess a fundamental forgetfulness, a capacity to erase its own past, which challenges the very notion of scientific inquiry, for if the past can be obliterated, then the laws we deduce from observation might be provisional, contingent, and ultimately unreliable. Recent developments in the study of gravitational waves and black hole mergers have added new layers to the mystery, as observations from LIGO and Virgo provide data that might one day test these competing theories. Yet the core paradox remains unresolved, a stark reminder that our two most successful physical theories, general relativity and quantum mechanics, are incompatible at the most extreme scales. The black hole information paradox forces us to confront the possibility that space-time itself is not fundamental, that it emerges from more basic quantum entanglements, that what we perceive as solid, continuous reality is a coarse-grained approximation of a far stranger, more fragmented substrate. It suggests that the universe might be fundamentally computational, that information is the primary substance of existence, and that black holes represent not just gravitational collapse, but a breakdown of the code that renders reality. As we stand on the precipice of a new understanding, peering into the abyss of these cosmic enigmas, the paradox serves as both a warning and an invitation, challenging us to rethink everything we believe about space, time, and the nature of existence itself. The silence of the singularity may yet hold the key to unlocking a deeper theory, one that reconciles the quantum with the cosmic. But until then, the information remains lost, or perhaps hidden in plain sight, waiting for a mind capable of deciphering the language of the void.
Number 4. The Boltzmann brain paradox. Are you just a fluke of entropy? In the cold, expanding void of a universe trending toward maximum entropy, where stars burn out and matter decays into a featureless sea of particles, a disturbing statistical possibility emerges from the equations of thermodynamics and quantum fluctuation. It is known as the Boltzmann brain paradox, named after the physicist Ludwig Boltzmann, who first grappled with the implications of entropy and the arrow of time in the late 19th century. The paradox arises from a simple yet profound observation. If the universe is eternal, or if it exists in a state of thermal equilibrium for an infinite duration, then random quantum fluctuations will inevitably produce ordered structures, however improbable. Among these structures, the simplest self-aware entity is not an entire cosmos with billions of galaxies, but a single isolated brain, complete with false memories and sensory impressions, spontaneously assembling from the chaos of the void. This hypothetical construct, the Boltzmann brain, would believe itself to be an ordinary observer in a vast, ancient universe, when in reality it is a momentary flicker of consciousness, destined to dissolve back into randomness within a fraction of a second. The terrifying implication is statistical. If such fluctuations are possible, then Boltzmann brains should vastly outnumber ordinary observers like us, who arise through the slow, improbable process of cosmic evolution and biological development. Therefore, if we assume that we are typical observers, the most probable explanation for our conscious experience is that we are not real beings in a real universe, but fleeting hallucinations of the vacuum, mistaken about everything we perceive. This paradox challenges the very foundation of empirical science, for if our memories and observations cannot be trusted, if the past we recall might be an illusion implanted by a random fluctuation, then no knowledge is secure, no experiment is meaningful, and the entire edifice of human understanding collapses into solipsistic uncertainty.
Physicists have attempted to resolve this nightmare scenario by proposing that the conditions necessary for Boltzmann brains to form are not actually met in our universe, that the timescales required for such fluctuations exceed the lifespan of the cosmos, or that the nature of dark energy and cosmic acceleration prevents the thermal equilibrium necessary for these random assemblies. Others argue that the paradox reveals a fundamental flaw in our application of probability to cosmology, that the measure problem in eternal inflation renders such comparisons meaningless, or that consciousness itself cannot arise from mere statistical accidents, requiring a continuous embodied history that a momentary brain cannot possess. Yet none of these solutions are entirely satisfactory, and the Boltzmann brain remains a ghost in the equations, a reminder that our most successful theories of physics, when extrapolated to their logical extremes, can produce conclusions that are indistinguishable from madness. The paradox also intersects with philosophical questions about the nature of reality and the reliability of perception. If a Boltzmann brain can have the exact same subjective experience as a human being, then what distinguishes reality from illusion? Is consciousness merely a pattern of information, regardless of its substrate or history, or does it require a causal connection to a wider world? These questions are not merely academic, they strike at the heart of what it means to know anything at all. In a universe governed by chance and entropy, the emergence of order is already miraculous, but the emergence of a mind that can question its own existence is perhaps the greatest anomaly of all. The Boltzmann brain paradox forces us to confront the possibility that our sense of continuity, our belief in a stable external world, and our confidence in the laws of physics might be nothing more than a convenient story told by a random fluctuation, a story that ends as abruptly as it began. As cosmologists refine their models of the early universe and the ultimate fate of space-time, they must also grapple with this unsettling implication that the very act of observation, the foundation of science, might be a brief spark in an endless night with no deeper meaning or purpose. The paradox does not offer comfort, it offers only a mirror, reflecting back the fragility of our assumptions and the profound mystery of consciousness itself. In the end, the question remains, are we the product of a long, intricate history written in the stars, or are we merely a thought that the universe is having, a thought that will vanish before it can finish itself? Number 5. The twin paradox, the illusion of simultaneity. In the realm of special relativity, time ceases to be the universal constant that Newtonian physics once proclaimed, transforming instead into a malleable dimension that bends and stretches depending on the observer's state of motion. This unsettling revelation gives rise to one of the most enduring and counterintuitive puzzles in modern physics, the twin paradox. Imagine two identical twins, one of whom embarks on a journey through space at a velocity approaching the speed of light, while the other remains on Earth. According to Einstein's equations, time for the traveling twin will pass more slowly relative to the sibling who stays behind, a phenomenon known as time dilation, verified countless times by atomic clocks on fast-moving aircraft and satellites. When the traveler eventually returns, they will have aged less than their earthbound counterpart, perhaps by years or even decades, depending on the speed and duration of the voyage. The paradox emerges when we consider the symmetry of relative motion. From the traveler's perspective, it is the Earth that moves away at relativistic speed. So why should the earthbound twin be the one who ages more? The resolution lies in the fact that the traveling twin must accelerate to turn around and return home, breaking the symmetry and introducing a non-inertial reference frame that general relativity accounts for. But the deeper implications ripple far beyond mere mathematical consistency. This paradox forces us to confront the unsettling truth that there is no universal now, that simultaneity is relative, that two events which appear simultaneous to one observer may occur at different times for another, depending on their velocity and gravitational environment. The philosophical ramifications are profound. If time is not absolute, then the distinction between past, present, and future may be an illusion of human perception, a cognitive artifact rather than a fundamental feature of reality. Some physicists, following the block universe interpretation, argued that all moments in time exist simultaneously, that the flow of time is a subjective experience, and that the universe is a static four-dimensional manifold where birth, life, and death are equally real, equally present, merely located at different coordinates along the temporal axis. In such a view, the twin paradox is not a puzzle to be solved, but a window into the true nature of existence, where free will is an illusion, where every decision has already been made, where the future is as fixed as the past. Others contend that the paradox reveals a deeper mystery about the nature of consciousness and its relationship to time, that the experience of temporal flow might be emergent, arising from quantum processes in the brain that are not fully described by relativistic physics. The twin paradox also intersects with the possibility of time travel to the future, a one-way journey that is not only theoretically permissible, but routinely accomplished by particles in accelerators and astronauts on the International Space Station, albeit on minuscule scales. Yet the asymmetry of the effect, the fact that one can travel to the future but not return to the past without invoking exotic matter or closed time-like curves, suggests that time possesses an inherent directionality, an arrow that points from order to disorder, from lower to higher entropy, even as the underlying equations of physics remain time-symmetric. This tension between the reversible laws of fundamental interactions and the irreversible experience of macroscopic reality remains one of the deepest unsolved problems in theoretical physics. As we push the boundaries of technology, as we contemplate interstellar voyages that would require relativistic speeds, the twin paradox ceases to be a mere thought experiment and becomes a practical consideration for the future of humanity. The psychological impact on travelers who return to a world where everyone they knew has aged or died cannot be overstated, raising ethical questions about the cost of exploration and the nature of human connection across temporal divides. Moreover, the paradox challenges our intuitive understanding of identity and continuity. If one twin ages more slowly, are they still the same person, biologically and psychologically, as their sibling? Does time shape the self in ways that mere chronological age cannot capture? The twin paradox, therefore, is not just a curiosity of relativistic mechanics, but a profound meditation on the nature of time, identity, and reality itself. It reminds us that the universe is far stranger than our everyday experience suggests, that the fabric of space-time is woven with threads of mystery that defy common sense, and that our quest to understand the cosmos must ultimately grapple with the enigma of our own existence within it. As we peer deeper into the relativistic realm, we are forced to relinquish the comforting illusion of a universal clock ticking away the moments for all observers, and instead embrace a reality where time is personal, where every journey through space is also a journey through time, and where the very notion of now is a fragile, local phenomenon, contingent on the path we have taken through the four-dimensional tapestry of existence.
Number 7. Maxwell's Demon, the Paradox of Entropy and Information.
In the mid-19th century, as the laws of thermodynamics were being forged in the fires of industrial revolution, a thought experiment emerged that would haunt the foundations of physics for over a century, challenging the very notion of irreversibility and the arrow of time. It was conceived by James Clerk Maxwell, one of the greatest minds in scientific history, who imagined a microscopic being capable of sorting fast-moving molecules from slow-moving ones without expending energy, thereby violating the second law of thermodynamics. This hypothetical entity, later dubbed Maxwell's demon by Lord Kelvin, stands at the gate between two chambers of gas, observing individual molecules and allowing only the swift to pass in one direction and the sluggish in the other. Over time, one chamber grows hot, the other cold, creating a temperature gradient from an initially uniform system, a process that appears to decrease entropy without performing work, effectively constructing a perpetual motion machine of the second kind. The paradox struck at the heart of statistical mechanics, suggesting that the laws governing heat and energy might not be absolute, but probabilistic, vulnerable to manipulation by an intelligent agent with perfect information. For decades, physicists struggled to exorcise the demon, proposing that the act of measurement itself must incur an entropy cost, that the demon's memory would eventually fill with information about molecular speeds, and that erasing this memory to continue operating would generate enough waste heat to preserve the second law. This insight, pioneered by Leo Szilard in 1929 and later refined by Rolf Landauer and Charles Bennett, forged a profound link between information and thermodynamics, revealing that information is not abstract but physical, that bits have mass, energy, and entropy, and that the processing of knowledge is subject to the same constraints as the movement of matter. The resolution, however, only deepened the mystery, for it implied that the universe is fundamentally computational, that reality might be constructed from information, and that consciousness, observation, and knowledge play an active role in shaping the behavior of physical systems. If a demon with perfect information can seemingly reverse entropy, then what does this say about the nature of time itself? Is the arrow of time merely a consequence of our ignorance, of the practical impossibility of tracking every particle in a complex system? Some theorists argue that the second law is not a fundamental law at all, but an emergent property of large numbers, a statistical tendency that holds only because we lack the computational power to reverse it, that in principle, with sufficient knowledge and control, entropy could be locally reduced, time's flow reversed, and the past reconstructed from the present. This possibility intersects with the black hole information paradox and the holographic principle, suggesting that the total information content of a region of space is proportional to its surface area, not its volume, implying that the three-dimensional world we experience might be a projection of two-dimensional data encoded at its boundaries. Maxwell's demon thus becomes a gateway to questions about the ultimate nature of reality. Is the universe a giant computer, processing information according to fixed rules? Is consciousness a thermodynamic process, a localized decrease in entropy sustained by the consumption of free energy and the export of waste heat? The paradox also has practical implications for the future of technology, as engineers push toward the fundamental limits of computation, where the energy cost of erasing a single bit becomes a critical constraint, where quantum computing exploits superposition and entanglement to perform calculations that would be impossible for classical machines, and where the boundary between information and matter blurs. Recent experiments with nanoscale systems and feedback control have begun to realize versions of Maxwell's demon in the laboratory, using single electrons, photons, and atoms to demonstrate that information can indeed be converted into work, that knowledge has thermodynamic value, and that the demon is not merely a philosophical curiosity, but a blueprint for future technologies. Yet the core enigma remains. Why does the universe appear to favor disorder? Why does time flow in one direction? And what role does observation play in this process? The demon forces us to confront the possibility that entropy is not an objective feature of the world, but a measure of our subjective ignorance, that the distinction between past and future might be contingent on the perspective of the observer, and that the laws of physics, as we understand them, might be incomplete without a theory of information and consciousness. As we stand on the threshold of a new scientific revolution, where quantum mechanics, relativity, and information theory converge, Maxwell's demon serves as a reminder that the deepest mysteries of the cosmos may not be found in the distant stars, but in the intimate relationship between knowledge, energy, and existence. The demon does not offer easy answers. It offers a challenge, inviting us to rethink the foundations of physics, to question the inevitability of decay and disorder, and to imagine a universe where information is the primary substance, where consciousness is not an epiphenomenon but a fundamental force, and where the arrow of time might be reversible, not in practice, but in principle. In the end, the paradox remains a testament to the power of human imagination, a thought experiment that continues to inspire, to provoke, and to illuminate the path toward a deeper understanding of the reality we inhabit, a reality that may be far more malleable, far more interconnected, and far more mysterious than we have ever dared to believe.
Number 7. Maxwell's demon. The paradox of entropy and information. In the mid-19th century, as the laws of thermodynamics were being forged in the fires of industrial revolution, a thought experiment emerged that would haunt the foundations of physics for over a century, challenging the very notion of irreversibility and the arrow of time. It was conceived by James Clerk Maxwell, one of the greatest minds in scientific history, who imagined a microscopic being capable of sorting fast-moving molecules from slow-moving ones without expending energy, thereby violating the second law of thermodynamics. This hypothetical entity, later dubbed Maxwell's demon by Lord Kelvin, stands at the gate between two chambers of gas, observing individual molecules and allowing only the swift to pass in one direction and the sluggish in the other. Over time, one chamber grows hot, the other cold, creating a temperature gradient from an initially uniform system, a process that appears to decrease entropy without performing work, effectively constructing a perpetual motion machine of the second kind. The paradox struck at the heart of statistical mechanics, suggesting that the laws governing heat and energy might not be absolute, but probabilistic, vulnerable to manipulation by an intelligent agent with perfect information. For decades, physicists struggled to exorcise the demon, proposing that the act of measurement itself must incur an entropy cost, that the demon's memory would eventually fill with information about molecular speeds, and that erasing this memory to continue operating would generate enough waste heat to preserve the second law. This insight, pioneered by Leo Szilard in 1929 and later refined by Rolf Landauer and Charles Bennett, forged a profound link between information and thermodynamics, revealing that information is not abstract but physical, that bits have mass, energy, and entropy, and that the processing of knowledge is subject to the same constraints as the movement of matter. The resolution, however, only deepened the mystery, for it implied that the universe is fundamentally computational, that reality might be constructed from information,
and that consciousness, observation, and knowledge play an active role in shaping the behavior of physical systems. If a demon with perfect information can seemingly reverse entropy, then what does this say about the nature of time itself? Is the arrow of time merely a consequence of our ignorance, of the practical impossibility of tracking every particle in a complex system? Some theorists argue that the second law is not a fundamental law at all, but an emergent property of large numbers, a statistical tendency that holds only because we lack the computational power to reverse it, that in principle, with sufficient knowledge and control, entropy could be locally reduced, time's flow reversed, and the past reconstructed from the present. This possibility intersects with the black hole information paradox and the holographic principle, suggesting that the total information content of a region of space is proportional to its surface area, not its volume, implying that the three-dimensional world we experience might be a projection of two-dimensional data encoded at its boundaries. Maxwell's demon thus becomes a gateway to questions about the ultimate nature of reality. Is the universe a giant computer, processing information according to fixed rules? Is consciousness a thermodynamic process, a localized decrease in entropy sustained by the consumption of free energy and the export of waste heat? The paradox also has practical implications for the future of technology, as engineers push toward the fundamental limits of computation, where the energy cost of erasing a single bit becomes a critical constraint, where quantum computing exploits superposition and entanglement to perform calculations that would be impossible for classical machines, and where the boundary between information and matter blurs. Recent experiments with nanoscale systems and feedback control have begun to realize versions of Maxwell's demon in the laboratory, using single electrons, photons, and atoms to demonstrate that information can indeed be converted into work, that knowledge has thermodynamic value, and that the demon is not merely a philosophical curiosity, but a blueprint for future technologies. Yet the core enigma remains. Why does the universe appear to favor disorder? Why does time flow in one direction? And what role does observation play in this process? The demon forces us to confront the possibility that entropy is not an objective feature of the world, but a measure of our subjective ignorance, that the distinction between past and future might be contingent on the perspective of the observer, and that the laws of physics, as we understand them, might be incomplete without a theory of information and consciousness. As we stand on the threshold of a new scientific revolution, where quantum mechanics, relativity, and information theory converge, Maxwell's demon serves as a reminder that the deepest mysteries of the cosmos may not be found in the distant stars, but in the intimate relationship between knowledge, energy, and existence. The demon does not offer easy answers. It offers a challenge, inviting us to rethink the foundations of physics, to question the inevitability of decay and disorder, and to imagine a universe where information is the primary substance, where consciousness is not an epiphenomenon but a fundamental force, and where the arrow of time might be reversible, not in practice but in principle. In the end, the paradox remains a testament to the power of human imagination, a thought experiment that continues to inspire, to provoke, and to illuminate the path toward a deeper understanding of the reality we inhabit, a reality that may be far more malleable, far more interconnected, and far more mysterious than we have ever dared to believe.
Number 8. Schrödinger's cat. The paradox of superposition and collapse. In the shadowed corridors of quantum theory, where certainty dissolves into probability and the act of observation shapes the very reality it seeks to measure, there exists a thought experiment so unsettling that it has haunted physicists and philosophers for nearly a century. Erwin Schrödinger devised it in 1935 not as a proposal, but as a reductio ad absurdum,
a critique of the Copenhagen interpretation that suggested a quantum system remains in a superposition of all possible states until measured, at which point the wave function collapses into a single outcome. To illustrate the apparent madness of this idea, Schrödinger imagined a cat sealed in a steel chamber with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the counter triggers the hammer, breaking the vial and killing the cat. If it does not decay, the cat remains alive. According to quantum mechanics, until the box is opened and an observation made, the atom exists in a superposition of decayed and not decayed, which means the cat must simultaneously be both dead and alive, a grotesque hybrid of mutually exclusive states. This paradox was intended to expose the absurdity of applying quantum principles to macroscopic objects, yet decades of experimental verification have only deepened the mystery, confirming that superposition is real, that particles can indeed occupy multiple states at once, and that the boundary between the quantum and classical worlds remains frustratingly elusive. The measurement problem, as it has come to be known, asks a deceptively simple question: what constitutes an observation? Is consciousness required to collapse the wave function, as some early interpreters suggested, or is it sufficient for a particle to interact with any macroscopic system, any environment capable of recording information? Decoherence theory offers a partial answer, proposing that quantum superpositions are not truly collapsed, but become entangled with their surroundings, effectively hiding interference effects through environmental interaction, making the system appear classical to any local observer. Yet this explanation merely pushes the problem back a step, for it does not resolve why we experience a single definite outcome rather than a branching multiplicity of realities. The many worlds interpretation, championed by Hugh Everett, takes the mathematics at face value, asserting that all possible outcomes actually occur, each in its own newly branched universe, so that the cat is both dead and alive, but in separate, non-communicating realities. This solution preserves the unitary evolution of the wave function without collapse, but at the staggering cost of infinite ontological proliferation, a multiverse where every quantum decision spawns countless copies of existence, each as real as our own. Other interpretations, such as objective collapse theories, propose that wave functions spontaneously localize after a certain time or mass threshold, introducing a fundamental randomness that breaks unitarity but restores a single objective reality. Still, no consensus has emerged, and the paradox remains a live wire in the foundations of physics, challenging our understanding of causality, identity, and the nature of consciousness itself. If superposition applies to all matter, then why do we not experience macroscopic objects in multiple states? Is there a scale at which quantum weirdness gives way to classical certainty, or is the appearance of definiteness an illusion, a cognitive artifact of brains evolved to navigate a middle world of medium-sized objects? Recent experiments with increasingly large molecules, even tiny mechanical oscillators, have demonstrated quantum behavior at scales once thought impossible, blurring the line between the microscopic and macroscopic, suggesting that Schrödinger's cat might not be as absurd as it first appeared. The paradox also intersects with the philosophy of mind, raising questions about the role of the observer. If consciousness collapses the wave function, then does reality depend on being perceived, implying a participatory universe where mind and matter are inextricably linked? Or is consciousness itself a quantum process emerging from superpositions within neural microtubules, as Roger Penrose and Stuart Hameroff have controversially proposed? These speculations remain unproven, but they underscore the profound implications of the measurement problem for our understanding of self and world. The cat in the box is more than a pedagogical device. It is a mirror reflecting our deepest uncertainties about the nature of existence. In a universe governed by quantum laws, reality may not be fixed until it is observed, meaning that the past itself might be indeterminate, subject to revision by future measurements, a notion that challenges the very foundation of historical truth and scientific objectivity. Some physicists argue that the paradox reveals a fundamental limitation of human language and intuition, that we are trying to describe a reality that operates on principles fundamentally alien to our evolutionary experience, and that the only honest response is to accept the mathematics without demanding a classical narrative. Yet the human mind craves coherence, a story that makes sense, and so the interpretations multiply, each offering a different resolution, none entirely satisfying. Schrödinger's cat, therefore, stands as a monument to the limits of knowledge, a reminder that the universe may be stranger than we can conceive, that the act of knowing may alter the known, and that the quest for a complete description of reality may ultimately require us to transcend the categories of thought that have served us for millennia. As quantum technologies advance, harnessing superposition and entanglement for computation and communication, the paradox ceases to be merely philosophical and becomes practical, forcing engineers and scientists to grapple with the foundations of the systems they build. In the end, the cat remains both dead and alive, not in a box of steel, but in the liminal space between question and answer, between mystery and understanding, inviting us to peer into the abyss of quantum reality and confront the possibility that the world is not as it seems, that certainty is an illusion, and that the truth may be far more wondrous and far more unsettling than we ever imagined.
Number 9. The Grandfather Paradox, the impossibility of changing the past. The allure of time travel has captivated the human imagination for centuries, promising the power to rewrite history, to correct past mistakes, to witness the dawn of civilization or the extinction of the dinosaurs. Yet beneath this seductive fantasy lies a logical trap so profound that it may render the very concept of backward time travel impossible, or at least constrain it to a rigid, unchangeable script where free will is an illusion. This is the Grandfather Paradox, a thought experiment that exposes the violent contradiction inherent in the idea of altering the past. Imagine a traveler who journeys back in time and, whether by accident or design, prevents their grandparents from meeting, thereby ensuring that one of their parents is never born, which means the traveler themselves is never conceived. But if the traveler is never born, how could they have existed to travel back in time and interfere with their grandparents' meeting in the first place? The paradox creates a logical loop with no consistent resolution, a causal contradiction that violates the fundamental principle of non-contradiction upon which all rational discourse depends. This is not merely a puzzle for science fiction writers. It represents a genuine challenge to any physical theory that permits closed time-like curves, solutions to Einstein's equations that allow world lines to loop back upon themselves. Physicists have proposed several mechanisms to resolve the paradox, each with unsettling implications. The Novikov self-consistency principle, for instance, asserts that the laws of physics simply prevent any action that would create a logical inconsistency. The gun jams, the traveler misses, or some other improbable event intervenes to ensure that history remains unchanged. In this view, time travel is possible, but only as a passenger on a predetermined track, where every attempt to alter the past was always part of the past, preserving a single consistent timeline. This resolution, however, comes at the cost of free will, suggesting that our choices are illusory, that the future is as fixed as the past, and that the sensation of making decisions is merely the unfolding of a script written in the geometry of space-time.
Another solution, drawn from the many worlds interpretation of quantum mechanics, proposes that any attempt to change the past does not alter the traveler's original timeline, but instead branches off a new parallel universe, one where the grandparents never meet and the traveler is never born, while the original timeline remains intact. In this multiverse scenario, the paradox is avoided because the contradiction never occurs within a single reality. The traveler simply moves from one branch of the wave function to another, leaving their own history untouched. Yet this resolution raises profound questions about identity and moral responsibility. If the traveler kills their grandfather in a parallel world, have they committed murder or merely altered a copy of reality? And if every decision spawns a new universe, does any choice truly matter? Or are all possibilities equally real, equally inevitable? Some theorists argue that the grandfather paradox is proof that backward time travel is fundamentally impossible, that the universe possesses a chronology protection conjecture, as Stephen Hawking termed it, which prevents the formation of closed time-like curves through quantum effects that destabilize any potential time machine. This would mean that the arrow of time is not merely a statistical tendency, but a fundamental feature of reality, that causality is inviolable, and that the past is forever sealed off from intervention. The paradox also intersects with philosophical debates about the nature of time itself. Is the past fixed and unchangeable, a block of events that exists eternally? Or is it malleable, subject to revision by actions in the present? If the former, then time travel, even if possible, would be a journey of observation, not intervention. If the latter, then the grandfather paradox suggests that such intervention leads to logical absurdity, implying that the universe must possess mechanisms to prevent it. Recent developments in quantum information theory have added new layers to the discussion, with proposals that quantum particles might be able to travel back in time in a limited sense, interacting with their past selves in ways that preserve consistency through quantum entanglement and superposition. These experiments, conducted with photons and quantum circuits, suggest that the paradox may be resolved at the microscopic level through the peculiar logic of quantum mechanics, where contradictions can coexist in superposition until measured. Yet scaling these effects to macroscopic objects, to human beings, remains a distant and perhaps impossible dream. The grandfather paradox therefore stands as a sentinel at the boundary of the possible, a reminder that the universe may not permit the rewriting of history, that causality is a law more fundamental than gravity or electromagnetism, and that our desire to change the past may be a longing for a power that reality simply does not grant. It forces us to confront the possibility that time is not a river we can navigate upstream, but a landscape we can only traverse in one direction, that every moment, once passed, is forever beyond our reach, and that the only time we truly possess is the present, fleeting and fragile, the only point where action and consequence can still meet. As we continue to explore the mysteries of space-time, the paradox remains a crucial test for any theory of time travel, a logical filter that separates plausible speculation from impossible fantasy, and a humbling reminder that some doors, once closed, may never be opened again.
Number 10. The Andromeda Paradox, the illusion of the present. In the relativistic universe revealed by Einstein, the concept of now fractures into countless personal timelines, each valid for its observer, yet irreconcilable with any universal standard. This unsettling truth finds its most profound expression in the Andromeda Paradox, also known as the Reitdijk-Putnam argument, a thought experiment that demonstrates how two people walking past each other on a city street can, according to the laws of special relativity, disagree on what is happening at this very moment in the Andromeda galaxy, 2.5 million light-years away.
For one observer, an alien civilization in Andromeda may have already launched an invasion fleet toward Earth. For the other, the decision to launch has not yet been made, the future still unwritten, the outcome suspended in quantum uncertainty. Both perspectives are equally valid, equally real, dictated solely by their relative motion through space-time. This paradox strips away the comforting illusion of a shared present, revealing that simultaneity is not a feature of the cosmos, but a cognitive artifact, a useful approximation for slow-moving creatures on a small planet, but fundamentally false at the scale of the universe. If what is now in Andromeda depends on your velocity, then the entire history and future of that galaxy must already exist in a static four-dimensional block, where past, present, and future are equally real, equally fixed, merely located at different coordinates along the temporal axis. This block universe interpretation, forced upon us by the mathematics of relativity, suggests that free will is an illusion, that every decision you will ever make has already been made, that the sensation of temporal flow is a trick of consciousness, a narrative spun by brains evolved to navigate a world where relativistic effects are negligible. The Andromeda paradox thus becomes a gateway to existential questions. If the future is as real as the past, then why do we experience time as a river carrying us forward? Is consciousness a process that moves through the block, illuminating moments sequentially, or is the movement itself an illusion, with all moments of awareness existing eternally in their respective locations? Some physicists argue that the paradox reveals a deeper truth about the nature of reality, that space-time is not fundamental but emergent, that the block universe is a mathematical convenience rather than an ontological description, or that quantum indeterminacy preserves an open future despite relativistic constraints. Yet no resolution has gained consensus, and the paradox remains a stark reminder that our intuitive understanding of time is profoundly mistaken. The implications extend beyond philosophy, into the realm of human experience. If the future is fixed, then hope, regret, ambition, and fear are emotions based on a false premise, stories we tell ourselves to make sense of a reality we cannot control. This does not necessarily negate the value of those experiences. They may be essential to the structure of consciousness, but it challenges the notion that our choices shape what is to come. The Andromeda paradox also intersects with the measurement problem in quantum mechanics, raising the question of whether wave function collapse is relative to the observer, whether different observers can legitimately disagree on whether a quantum event has already occurred in a distant part of the universe. Recent experiments testing relativistic quantum information have begun to probe these questions, but the core mystery endures. How do we reconcile the subjective flow of time with the objective geometry of space-time? The paradox forces us to confront the possibility that reality is not a story unfolding, but a landscape already complete, that our journey through life is not a creation, but an exploration of a territory that has always existed. This vision is both liberating and terrifying. Liberating because it suggests that every moment of joy, every act of love, every instance of beauty is eternally preserved in the fabric of existence. Terrifying because it implies that suffering, loss, and injustice are equally permanent, equally unchangeable. As we stand on the threshold of a new understanding where quantum gravity may finally unify the principles governing the very small and the very large, the Andromeda paradox serves as a beacon of the unknown, a reminder that the universe may be far stranger than our senses suggest, that time may not be what we think, and that the quest to comprehend reality may ultimately require us to transcend the very categories of thought that define our humanity. In the end, the paradox does not offer closure, it offers a mirror, reflecting back the limits of our perception, the fragility of our assumptions, and the profound mystery of existence itself. We are left with a question that echoes through the corridors of physics and philosophy. If the present is an illusion, then what are we, who experience it so vividly, so urgently? The answer, if it exists, may lie not in equations or experiments, but in a deeper understanding of consciousness, of the relationship between mind and cosmos, of the reason why a universe governed by impersonal laws should give rise to beings who can question their own place within it. Until then, the Andromeda Paradox remains a testament to the power of human curiosity, a thought experiment that continues to challenge, to inspire, and to illuminate the path toward a truth that may forever remain just beyond our grasp, a truth that whispers from the distant stars and the quiet depths of our own minds that reality is not what it seems, that time is not what we feel, and that the greatest mystery of all may be the fact that we are here at all, asking the question.